This is part of a presentation we had given at the Passive House conference, and some of you may have seen Katrine Klingenberg, the director of Passive House in the U.S., give a talk here. This talk will kind of build upon the conditions required for those sorts of homes. So both straw bale house seminar also occurred here, and I think there were some other seminars on energy efficient buildings. So this one will be looking at what's required to condition those sorts of buildings, and then our design work as far as interest in energy efficiency and building a system that's going to take care of the conditioning of these special types of homes. So the talk's actually called Design and Operation of a Conditioning Energy Recovery Ventilator. So this is the name we've given to our system that we're working on developing. And as I said, this is part of a presentation then that we've given at the Passive House conference past November up in Duluth, Minnesota. This is a picture of our lab here we moved into after the research park. And 6 months ago, this summer, we put in a 3.2 kilowatt PV system. It's a standalone 2-axis tracking system, and it gives us about 5,000 kilowatt hours a year of energy. So maybe a third or so less of our building's requirements. It's a 4,500 square foot lab building. Another thing in this picture, I'm right here on a ladder harvesting hops, which besides being an ingredient for brewing beer, one of our hobbies, it also provides nice shade in the summer for a building. So keeping that solar radiation, additional loading out of the house. When you harvest it in the fall, you cut it down to the ground, letting that solar radiation then help you as you're conditioning the building through the winter. So what's our motivation and objectives for doing this work? We're combining our knowledge of HVAC systems with our interest in energy efficient homes to create a product that really can't be found, especially in the U.S. There's some in Germany, but they're expensive and hard to obtain. And then coupled with highly efficient house construction, like the Passive House standards or straw bale construction, that these conditioning systems are going to let you cost effectively turn that into a net zero energy building. So having a smart system that's lower capacity, then you need less PV panels and that. And the serve will be a primary component for efficiently conditioning these types of buildings. And then finally, we'll be building in Urbana this upcoming year a net zero energy house of our own, a solar powered home, to both demonstrate our technology as well as other technologies out there, that just showing that this sort of thing can be done here and now, and being transparent in that construction, showing the costs and both long-term, which are very important, but a lot of times overlooked. So we do, our bulk of our work is in consulting in HVAC related industries. So we work with customers on designing systems all the way from refrigerator systems, prototypes, automotive systems, stationary, large chiller systems. We do a lot of simulation as well as building the prototypes, testing, development, that sort of work. And since we're not tied down to a particular industry, this allows us to combine technologies that you would normally see together. So as an example, this military aircraft cooling cart, it's ground support equipment. So when they're performing maintenance on military aircraft, they hook a hose up and keep the electronics cool. And my dad's actually traveling, they're doing qualification testing on this unit right now, but this company contacted us to do some development work, and we were able to bring technologies from automotive systems, stationary systems, large chiller systems, combine them together into something that they'd never really thought of before, but it gives them advantages of being very flexible, operating in Abu Dhabi or Antarctica, smaller compact system, as well as much more energy efficient. So this sort of thing is the same thing we'll be translating into our system that we're developing. So first I'll just go through some characteristics of energy efficient homes and the building requirements for these types of homes, and then looking at our product and the development, its operation, and some performance data. Keeping comfortable is made up of a lot of different things, and you need to look at the picture as a whole. There's building construction, what are the techniques used, what materials have been used in the building. The outside conditions have a large effect. Interior components. This consists of what appliances are in your building, how many people are there, and then the activities going on inside that building. So taking showers, exercising, things of that nature. Basically anything you're doing inside a home is going to be either adding heat or moisture to that space. An example of one of these energy efficient homes, and I know we have some team members here today, people have worked on the house, is the Decathlon house from the University of Illinois from 2007. This is a net zero energy house. All of its energy is provided by solar PV panels. In addition to that, it also allows 10,000 miles a year of electric vehicle transportation, which is quite a bit. And if you think about that, it's only basically 100 square feet or so of PV area that's needed to do that. Some characteristics of these types of homes then are that it significantly reduces the capacity requirements of systems. So we'll look at this more later, but these systems need to be very small. The loads on these buildings aren't very big. What's happening outside isn't necessarily being communicated to the interior space. And this makes ventilation and moisture management extremely important. And if you do this, and many people have found out the hard way, if you don't manage these things properly, you're going to see a mold, mildew, condensation on the inside of your house. So this is one of the main differences and an important point. And then while smaller, these systems must be more nimble and have smarter controls than a normal system. They need to be integrated and talking with the ventilation and moisture management system. So as opposed to on or off for your furnace or air conditioner, these systems need to know what's happening with ventilation. It needs to be actively controlled. Just looking at PV panel area versus insulation, may be surprising that the optimum is a fairly flat solution, that you can have thick insulation in your walls and require relatively little PV panel area, or you can have small insulation in your walls, but requires much larger area of PV panels. So it's roughly all over $40,000, but there's other things to consider as well. What happens if there's a problem with your PV system? Well, more insulation means your house will stay conditioned longer, as well as the size of the conditioning system and the efficiency. If it's having to deal with a wide range of conditions, you're going to need a much larger system. And with conventional systems, they're much less efficient, so you're going to be using more energy that way. Now, within these homes, I was talking about the ventilation and moisture management. There's two components to conditioning a house. You have sensible load, which most of you are familiar with, just changing the temperature. But then you also have the latent load, and that refers to this moisture. And both become very important. Conditioning a house going from 70 to 85 degrees, it takes the same amount of energy to reduce the relative humidity from 60 to 40% at 70 Fahrenheit. So there's a lot of energy that's going to be needed to do this moisture management as well. And just an overall then picture of the differences between the conventional versus efficient. Conventional homes are more dominated by the exterior conditions. What's the weather like outside? This is due to several factors: a leaky envelope, which is inherent in conventional construction techniques, that running wires and poking into your insulation, these holes all contribute to a leakiness, and basically this is a free exchange of conditioned and unconditioned air within your house. You don't have any control over this ventilation. That leads to not really being able to control the moisture as well. It's dominated by the outside. And so you're going to be using a larger capacity system because of this free air movement between the outside and indoor. Contrasting that to efficient homes, it's more balanced towards the interior load. So how many people are inside the house, what's going on inside. Ventilation and moisture then are actively controlled and monitored. And then small energy loads make energy recovery very significant. So if you're going to be actively ventilating, you want to, with a small load, be able to take back into your house the heat that you've put into conditioned air that's being exhausted outside. So that starts to become more important as well. Looking at conventional conditioning systems for places like Illinois, usually they'll size or oversize it, I should say, for the square footage of your house. So for a few thousand square foot home, you'll have about a 3-ton air conditioner, about 10 kilowatts. In its design, roughly 2/3 of this is designed for the sensible or bringing the temperature down, and about 1/3 of it is for the latent loads or dehumidifying the air. Conventional gas furnace, just over 20 kilowatts for heating. And the main reason for these systems to be oversized is that it needs to span these wide ranges of conditions that these houses that are not well insulated or sealed are going to be seeing. And this makes control of the capacity of these systems very difficult, and they're either on or off systems. You have programmable thermostats in that to help a little bit, but really there's not much capacity control within those systems. So what we'll be looking at here is a simulation done in Excel. This is a base case house here. It's an existing home in Urbana that we've based it off of. It's 2,000 square foot house. It's ICF, insulated concrete form construction, so well-sealed home, a good amount of insulation, high-performance windows. The ventilation, 0.2 air changes per hour, so that amount of the air within the house within an hour needs to be ventilated. We're going to assume 4 people, both adding heat as well as moisture to the house, 75 watts each. And then about 200 watts of just other internal generation of heat. So looking at this with weather data, this is taking weather data for this region of the country throughout the year, looking at the high and low temperature for each day. And you can see for Illinois, we just have the extreme. We have the worst of the worst. We have hot and humid weather in the summertime and extremely cold weather in the wintertime. So, but what you also see here is that the loads are relatively small for this type of house construction, energy efficient house, that our heating load, let me point that out, or this is our cooling load actually, will need from 1 to 2,000 watts. So where we saw that other system, conventional system, had a 10 kilowatt cooling capacity, this is very small. Heating wise in the winter, about 3,000 watts are needed to do, and that's mostly sensible load, just bringing that temperature up. And then in this kind of house, we see in this area here, the origin is roughly, I think, 50% relative humidity, 72 degrees Fahrenheit. So spring and fall time, really not much conditioning is needed within this type of home. And then comfort's kind of a squishy concept where some people may feel comfortable in one condition, others might not feel so comfortable. So this just shows a range in temperature and then humidity here that your system's going to have to deal with as far as where people are going to feel comfortable within the space. As far as then doing the same thing for a conventional home, we see that the loads on this home are about 3 times as much as the other home. So in the wintertime, we have about 10 kilowatts of heating needed, 3,000 to 4,000 for your cooling and dehumidification in the summertime. So a much broader span is going to be needed. So that's that larger capacity system that's going to be required. Now we've seen that these types of homes need active ventilation, moisture control. Be looking at then our system we're currently developing, the Serve. Picture of it, right? This is the first prototype, so a little bit of duct tape and cardboard, which we hope to get rid of most of that. But it's a low temperature heat pump, air source heat pump system. Compressor, there's a hot side and a cold side. It's basically, if you think about this as a window air conditioning unit that's completely inside your home. So some features of the Serve that then make it well suited for conditioning in these super insulated, super sealed homes are that it is a small capacity. That standard systems, it's hard to find very small. It's self-contained and it's a modular system. So based on the size of your house, you may put 2 or 3 of these together to build up to that. That modularity gives you capacity control, as well as it has variable speed compressor. So within each module, you're able to vary this compressor speed, which gives you additional adjustability to the load. And then within one self-sealed box, you're going to have heating, you're going to have cooling, dehumidification, and ventilation as well. So it combines all the things you need for this type of house conditioning into one package. Another important consideration, since it is a refrigerant-based system, is what kind of refrigerants go in. And this is kind of a snapshot of the history of refrigerants. R12 and R22 really aren't around much anymore. R22 you still see a bit of as they're trying to get rid of these systems as they're phasing out. Both of these have some ozone depletion and then fairly high global warming potential. So as things progress, R134A and 410A are coming in to replace these. So you can see there's no longer any ozone depletion from these refrigerants, but still significant global warming potential. And that's the next thing that needs to get knocked down. And we're phasing into some new refrigerants, one of which is CO2, being developed mainly for the automotive systems, so that'll be replacing 134A. And then there's a new refrigerant that's not quite out yet, 1234YF, and it's meant as a drop-in for the 134A system. The CO2 it's a unique fluid and it's a high-pressure refrigerant, so additional design and consideration needs to go into this to make it feasible as a refrigerant. And just looking at some of the regulations that have been put in place that are causing these changes. 94, R12 was banned and replaced with 134A, so see these in your cars and your refrigerators at home. R22 then, you're starting to see the 410A is really prevalent in your home residential air conditioning systems now as R22 is being phased out. And then the European Union, which is leading a lot of these changes, has a directive that's putting a standard on the GWP that's going to be needed at 150. And as we saw before, all of these are significantly higher than that 150. So our 134A and 410A at some point are going to be phased out. And so that's where then the CO2 and HFO, YF are coming into place. So with our system, we're starting out with a 134A base system, and our plan is then to use 1, 2, 3, 4 as a drop-in replacement. So this will give us the no ozone and then the very low global warming potential. The other thing about our system, as I said, it was self-sealed and self-contained, is very important. When you buy an air conditioning system, conventional for your house, it's a split system. So you have a condenser outside, you have your evaporator inside, and they're running refrigerant lines through the building. It's not only puncturing a hole in your building envelope and the insulation and ceiling, but this is where a lot of refrigerant leaks take place. So this is going to eliminate charging in line sets and fittings where these leaks take place, releasing it into the environment. It's a small refrigerant charge, is a small capacity system, self-contained, not long refrigerant lines running. And then it's sealed for the lifetime of the unit. So as the lifetime comes to an end, you can send the unit back and it can be safely recovered. We'll be taking a look here then at the modes of operation and some initial test results of the system. The modes are heating, cooling, heating with ventilation, so pulling fresh air inside, heating that air, and then using it to condition the space. Cooling with ventilation, as well as ventilation only, which is either ventilation or dehumidification. And so an important feature then is that these controls, as I was saying earlier, need to be smarter in dealing with all these different cases. So it needs to know how to switch between these different modes and which mode is the most efficient to be operating. So here's a schematic of heating without ventilation. So you're just recirculating the air with the inside space and taking outside air and expelling it back out. So we see here that the air is coming in 5.2. It's about a day like today. And we're recovering some of that outside, getting some heat from this outside air. And then our inside air is coming in about room temperature and coming out at 32, so enough to do some heating of the room. The compressor power in this case is 377 watts, and we're getting over 1,100 watts of heating capacity. So our coefficient of performance then is 3.1. We're getting 3 times the heating capacity. And this gives us an energy efficiency ratio of 11.1, another measure of performance. And you'll see units up to 20 EER out on the market today. They run these tests at a certain standard, which this one just at this happened to be at this condition. So we haven't compared to see what it actually would be. This is just some other data. This is on a winter day just below freezing. We can see the compressor powers right around 400, and we're getting anywhere from 11 to 1,200 watts of heating capacity. So about the same coefficient of performance. Another important consideration with our system, since it is air source heat pump, is defrosting. So it's much like your refrigerator, that the evaporator moisture is going to condense and freeze on that, and you're going to need at some point, as it restricts airflow and heat transfer, you need to get rid of that frost. So these are 2 defrost periods then that we instigated in the system, expelling that frost from the system. These are the temperatures. So we see just above freezing here is the outside air, and it's removing some heat, so it's coming out colder. And we're putting about 40-degree air in to the conditioned space. Once again, these are the defrost periods here. What we did in this control, and there's a few ways to do this, is took the air side air in then and put that over the evaporator, warming it up. And this time period was maybe from 5 to 10 minutes is what it appears it's going to take to do that. Here's the coefficient of performance. And here's another day. This day's pretty cold, so this past few weeks, this is newer data looking at here that it's been good as far as testing the system. So we see the capacity dropping, or the compressor power dropping here. That's a function of this drop-in mode control that the compressor we're using has its own control right now. We'll be developing our own control algorithm. The maximum is about 400, so we'd probably be up there in this case here. But as it is it's adjusting and doing its own thing. We're getting about 250 here and about just over 600 watts of heating capacity. And these are the temperatures, so we're still, even though it's cold, we're getting some heat from the outside air, and it's coming in 25, 27 degrees Celsius. So this is at 0 degrees Fahrenheit. We also ran it with that minus 17 degree day we had last week or so. The data is not shown for that, but it ran well. There was no damage to the system, so it's important to see that your refrigerant, you get liquid refrigerant back to the compressor, it can damage components. That it's been built properly so that we're not having any of those problems so far. And then this is the coefficient of performance again, around 2.5. And this here again is that drop-in mode control system that's kind of just doing its own thing right now. Cooling without ventilation, so same idea as the heating, but it's kind of like, this would be like a window air conditioner in your house, where the heating without ventilation, it's as if you took your window air conditioner and turned it around backwards. So here we're getting, the compressor power is 400 watts. We're getting just over a kilowatt of cooling capacity. The outside air is coming in, adding heat to that, taking heat out of our inside air, and returning it cooler. These conditions are just ones we've run in our lab, so we've had to do different things as far as taking the outlet air, aiming it towards the inlet to try to trick it into thinking it's a summer day and that. So the conditions aren't necessarily what you would actually see, but just trying to get it close, an idea of the capacity that we're seeing with it. And then here's that latent and sensible loading that was talked about earlier. So about 130 watts of latent, dropping moisture out, and then 940 watts of cooling that air down. This is heating with ventilation, so this is allowing fresh air to come into the unit. We're going to take inside air. We're going to remove some of the heat from that. So this is where the energy recovery then is being done. Outside air is coming in. We're adding that heat. It's coming in at 32 degrees, and then we're expelling this inside air cooler. So we have 330 watts, and our total heating capacity is 1803. So here we have quite a large coefficient of performance, and the energy efficiency is good as well. And then cooling with ventilation is the same way. Here we see a COP of 3.5, bit more latent, and then sensible loading there. And then ventilation mode. So it also can be done where the compressor's not on. If the control system sees what's coming into the unit, it can say, hey, I don't need to run the compressor. Or if you just purely want to dehumidify the inside air, just shown here, you're just running this over the evaporator, dropping moisture out. The tests we've run on have shown 0.5 liters per hour dropped out. Compressor power was 300 watts, so we had 1.5 liters of water per kilowatt hour were produced. Standard or Energy Star ratings for this standard size dehumidifier, which you might buy for your own home, needs to be greater than 1 liter per hour. So with this system, we're already quite a bit above that. Some other technologies then that can be incorporated into this unit be coupled with a ventless clothes dryer. It's also known as a condensing dryer. This is where you're not taking warm air to dry your clothes, but you're taking dehumidified air to dry your clothes. And it's a pretty efficient way to do that. So this air could be sent to your dryer, removing the moisture and recirculated to dry your clothes that way. So we've done a lot of testing, and the initial results look very promising. We've abused the unit quite a bit, and just trying to see what things are going to break or what things need to be improved. But so far they look really good. But there's still a lot to go. As you can see, test matrices expand very quickly as you're messing with different temperatures, humidities, airflow rates. So all these things make the controls very sophisticated. Another future option is a heat pump water heater, which you might have heard about, or more talk of them recently. GE announced that within the next few years they'll be releasing a commercial unit for sale. These give a COP of about 2 to 3, so where your electric resistance heating water heater has a COP of just 1, this is going to be 2 to 3 times better than that. Using this type of water heater, you also get cooling and dehumidification of your house, so that's an added benefit. So the serve would basically be here, circulating your inside air, and then instead of exchanging either heat with the outside or the inside, you're putting that into your hot water here. So with a COP of 3 and 15% PV panels, just comparing this to solar thermal, which a lot of people have an interest in as well, you get about 45% efficiency. So it's very similar to solar thermal system, but without the added complexity and holes being punctured into your building envelope. Some additional considerations that we have then with the system, we took a look at some of the data that showed those defrostings that occurred. So frost buildup will be a problem on the system, and it's something we're working on, the defrost strategy and sensing that and when to end that cycle. So it's an important consideration. Condensate removal is another one. Can we do anything, an added benefit with this? We spray it on condenser. Can we improve its performance? Is it worth doing that? Moisture, mold, and odor prevention. So when you're dealing with a warm, moist environment, you can easily grow things that you don't want. So making sure that there's none of that occurring in this will be very important. And then the end of the life cycle. What do you do with this thing when it's done? Looking at cradle to cradle. Can it be designed in a way that is an added benefit once it's done being useful? So with that, we've taken a look at what's needed for these energy efficient homes with super insulation. They're super sealed. These additional considerations that conventional systems just don't. They're oversized and not controllable in a manner that's useful for these types of homes. And then seeing our serve unit, what benefits we think it'll have as far as being used in these conditioning systems, and the results of that are looking good so far. So hopefully as we move further into development and both on the conditioning system as well as our zero energy house we'll be constructing, that maybe you'll have us back to give you an update on that and provide further information. So if there's any questions or anything, I'd be happy to try to answer. Yeah.
How do you decide your programs like condense and evaporation? Are you still kind of trying to figure it out?
It's most of the system. It's an existing system. So working with our contacts, it's one, and it's sized just about right. So we saw those building loads earlier on that simulation that one or two of these, with its modularity, it was sized just about right. So we're having a few kilowatts of heating and cooling capacity. So that's part of our investigation too, is just seeing how much capacity we're getting out of each system, and are these sized the way we want them to.
My curiosity was if you increase your core surface, then you could increase, kind of improve your COP.
Yeah, that's something we'll look at. The frost tolerance is an important issue. So I was talking about your refrigerator. If you look at that heat exchanger versus one in your air conditioner, there's quite a bit of difference. That any frost buildup restricts airflow and that. So that's an important consideration that we have here as well.
Can you comment on cooling with humidity and is it worth it to put in a dehumidifier in the summer?
So this will incorporate into that, and with the control of our system, that where we saw the conventional system, about 2/3 of it's designed for sensible and 1/3 of it for the latent load. This should have more flexibility to be able to shift that if you want more latent, just dropping the humidity out. But like the solar decathlon house, they won the climate conditioning event in that, and they did that with a separate system. So they had just a static air conditioner system along with a separate dehumidifier, just a Whirlpool one. And so that's a very effective way to do it, is having a separate one as well.
So it's worth it to put in a dehumidifier?
Yeah, definitely. Yeah, from the simulation results, you can get either by dropping moisture or temperature, you can move around that map to get to your comfortable level.
Because I was thinking both using electricity,
Mm-hmm.
which, I mean, does it use less electricity with the AC and the dehumidifier, or with just AC just by dropping the temperature?
I don't know for sure. Are you familiar with that, Clark?
Standard answer is that if your air conditioning system is well designed, you'll have pretty much the right balance of dehumidification and cooling. But if you've got too much airflow through it, you won't get much dehumidification. If you have too little airflow, clogged filter, that sort of thing, you'll get lots of dehumidification, and it'll be very inefficiently operating. So
That's the
it's hard to give a general answer. Sorry.
Oversized. The conventional systems are oversized that aren't able to do that dehumidification. It can be a big problem. So
Many of the modern systems are coming with fan speeds, multiple fan speeds on your indoor blower that can be adjusted by a mechanic. So there might be a switch for the summer and the winter to give you more comfort.
Do you envision this only for new construction, or do you think that there's any hope for the vast majority of houses that are already constructed?
Mostly for new construction, doing a retrofit, and I think if you hear Katrine speak about passive house and people trying to do retrofits that way, that you're basically tearing out the whole house and almost starting over. So it's not really cost effective to do a retrofit, deep retrofit that way. But in some cases, yeah, it can be used if the loads look like they'll be low enough for a retrofitted house. But mainly for starting with new construction, that it's a well sealed envelope is really important. So
the issue on retrofitting is really one of most houses aren't efficient enough keeping the envelope sealed and whatnot.
Mm-hmm.
Your loads to be right for you using this kind of product.
Yeah, and even there's what's called a blower door test, and you go around your outlets where they've drilled holes in the studs and that, running electrical and plumbing and that. Those, you're just killing your building envelope there. So keeping any sort of, you're paying to put all this insulation in, why you go back and dig it out and make voids in it, it's just a big problem.
How about on some of the extreme condition days? I mean, it looked like you guys were outputting 600 watts, but yet your chart is saying you might need 1,000 watts for a well-sealed home there.
Yeah, so the simulation was showing for the whole house as a whole. The data I was showing was just for the single module. So the modularity where it's just plugging them in, you have to look at your building size and that, and know how many of these modules to build up to that capacity.
So you might need 2 modules in that example.
Yeah.
For the 70-degree day.
Mm-hmm.
So are you still working on the way you get the unit to be smart about what conditions it's going to work towards? Whether it needs to be on speed to take care of
Yeah, so the data I show you is the work we've done most recently, just trying to assess the performance of it and its capacity. Moving into the next step now is controlling. We have the airflows we can control, as Clark was saying, to do that dehumidification. That's one way you can vary the airflow. Compressor speed also. So there's a lot of different variables that we're going to need to control, just running it at these different conditions, seeing which one is the most efficient way to do that. So yeah, as all these pieces come together, though, your matrix expands pretty quickly. So yeah.
Do you have any idea how much a single module would cost?
Not yet. That's something we're looking. I think is a smaller system. It should. I imagine the cost will be about the same what you pay per ton of cooling at the moment. But then considering the other things that go into it, we're looking at the ERV, whether this can provide that or if a separate one would be as well. So just taking a look at the things that are incorporated into it and how we want to position it that way. We're going to go into that consideration.
Question. When somebody's designing a building, will they have to have your system in mind? Or, is it sort of similar systems that will all be standard? You can choose, I guess, how much you need design and construction associated. It's a system that needs to be put into this kind of construction.
It would just get out of hand trying to put this in a regular constructed home. The loads are just too big. So it needs to be put in mind that the reason we're getting into this is that there currently isn't anything like this available. The solar house and another houses like that, Katrine's house here in Urbana, they use a mixture of different systems. So it might have an energy recovery ventilator. It might have its own dehumidifier, furnace, an air conditioner. So it's built up of 3 or 4 pretty efficient units for what they are, but nothing all in one that's going to take care of everything. So as far as getting those units to communicate with each other, that's something that they don't have that it's going to be difficult to do, but we think we can do it effectively.
The unit you're going to build in Urbana, what kind of construction will that be?
We're looking at ICF construction, and whether we add more insulation on top of the blocks. If you're not familiar with ICF construction, it's basically hollow Lego blocks that you fill with concrete. They're styrofoam blocks. So it provides its continuous barrier around the house, so there's no perforations in it. So that's construction. We're also looking at SIPs for the roof and that as well.
So it'll be slab on grade then?
Yeah, looking at slab as well.
Does the house have to be perfectly balanced? By this I mean that cooling capacity and heating capacity have to be the same order, or not? Does it have flexibility?
That's the thing about having the air source, then it doesn't need that. If you're looking at our lab building, which I showed in the first slide, has a geothermal heat pump in it. And Illinois, we're about right, where the heat you're going to be putting into the well is kind of a reservoir that you can take back out when you need it. So for ground source, it's a very important thing. But for these types of homes, ground source heat pumps, they're too complex, and the cost is pretty prohibitive from using those. So, but this doesn't need the balance like the ground source units do.